I'm from Duke University. I'm presenting our work, Longshot Indexing Growing Databases using MPC and Differential Privacy. This work involves joint effort from Joe Hess and my PhD advisors, Kartik and Ashwin. In today's data-driven world, large amounts of data are gathered, for example, using phones. They were processed and stored on the cloud due to its low cost and ease of maintenance. Recent news highlights lots of data breaches, emphasizing the urgency of secure databases on the cloud. These secure databases enable data encryption before uploading, so the cloud provider or adversary can only see encrypted data. Here is a general approach to build a secure database. We rely on cryptography technique called multi-party computation, or MPC, through which we have two non-colluding servers to compute on user data. Users can obliviously upload their data secret shared, due to which each individual servers on its own do not have access to the data other than the total data size. But together they have access to all data. Using MPC, the servers jointly can compute any functions. For instance, a predicted query that is submitted by analyst and return the query result. Analysts are categorized into untrusted analysts who can only get noisy results in plain text, and trusted analysts who can additionally get true and non-aggregate results that is secretly shared. While the servers faithfully execute MPC protocols, they are semi-honest, which means they attempt to learn information during query processing. Thus, the MPC protocols needs to use worst-case query execution to prevent leakage, for example, access pattern, or intermediate or output volume. For instance, using oblivious algorithm to hide access pattern with worst-case padding to hide volume, MPC protocols is fully private but incurs enormous performance cost. Other works based on hardware enclaves or structured encryption attempt to solve the performance problem by allowing the leakage. However, the leakage can lead to reconstruction of private data distribution. Recently, some works bridge the gap by allowing and unbounding the leakage with differentially private guarantee to prevent data reconstruction and provide a tunable balance between privacy and efficiency. Differential privacy provides a provable guarantee that one cannot reconstruct records in the input data set based on the output of differentially private algorithm. Specifically, for every pair of input D1 and D2 that differ in one row, adversary should not be able to distinguish between any D1 and D2 based on any output. The information leakage of the output is controlled using the privacy budget laws. Differentially private algorithms can achieve the property by perturbing the truth statistics using random noise sampled from Laplace distribution to release approximate statistics about the dataset. DP has been deployed in many real-world applications. Recent works to design secure protocols with DP leakage, they add DP noise to the statistics of leakage. For instance, they add DP noise to the number of access locations or the number of iterations to hide the access pattern. They add DP noise to intermediate or output volume or update size. Although these prior work offer controlled information leakage with DP guarantee, they are either too slow or not providing enough functionality. For instance, the first one will be too slow. The later ones have improved, but they either work on static data, rely on computations of a trusted data owner and cannot support multiple data owners, or support a specified query instead of arbitrary ad hoc queries. So can we use DP leakage to support more general settings? For example, answering ad hoc queries on growing data uploaded from multiple data owners. We designed Longshot to introduce DP leakage in storage and index level. By constructing and releasing differentially private data structures, Longshot can process unlimited ad hoc queries on the DP structures without complete privacy loss and avoid redundant computation on growing data and avoid relying on computation of a trusted data owner. To explain the DP structure, I'll use an example with 3 queryable beans and a query that wants to retrieve secret share records whose color is green. If I have a sorted data store with pointers to different beans, that makes query processing very efficient. Thus, we introduced two more structures, an index to keep the pointers and a synopsis for histogram to construct the index. If all of the information is in the clear, there may be too much information leakage and allows easy data reconstruction. So we use DP noise to perturb the synopsis to get a DP synopsis and DP index and release them in public. Then we construct DP store to ensure the number of records for each bean is the same as its DP count. The query processing is efficient because Longshot can answer queries on DP structures in public without MPC protocols. The leakage profile is differentially private, which is this DP synopsis. Next, we design system to update DP structures. Our system's overview began with triggering update to ingest the uploaded data periodically via a public timer. Once update is triggered, Longshot updates DP synopsis and use it to update DP store and DP index. Separately, Longshot processes query on DP structures that cover all uploaded data. We support point query and range query. The 2 servers only jointly execute protocols to construct DP structures. Other steps are performed without MPC. Next, I'll explain the oblivious algorithms to construct the DP structures. To construct DP synopsis, we compute true synopsis and add DP noise. To construct DP store, we design the protocol thresholded bean sort. In this example, the DP count for each bean is 462. So the number of records for each bean in DP store is also 462. We use 1 to denote real records and 0 to denote dummy records. Dummy records is indistinguishable from real records. When the DP count is larger than the true count for a bean, dummy records are introduced in the DP store. When DP count is smaller, real records are deferred to update. Before sorting, we need to pad a public number of dummy records for each bean with the input data. If the number of dummy is too large, the protocol is inefficient. If small DP store is inconsistent with the DP index, we use the insight that the number of dummy records in DP store is decided by the added noise in the DP synopsis. If we bound the added noise in synopsis with high probability, then we can use this number to choose the size of dummy records to pad enough, but not too many dummies. In addition to dummy records, we pad a counter record with DP count value for each bean and input. Then use 2 rounds of oblivious sort to generate DP store in the first part and move actual dummy and deferred data and counters to the end. In this figure, each node represents each data block uploaded at each triggered update. To update DP structure over time, we can simply apply the protocol on each disjoint data block. we call it as leaf approach. However, since we add random noise samples from Laplace distribution to synopsis, the variance of the added noise in synopsis is linear to the number of updates. So Laplace noise accumulates linearly in time in synopsis, leading to head errors over time. And the added dummy and deferred records accumulates linearly in time, leading to low efficiency. I'll explain two optimizations at no cost at privacy to ensure low errors of DP structures and high efficiency of updating DP structures. We choose to update DP structures on the root node of each subtree that the current update number belongs to. So the variance of added noise in DP synopsis is logarithmic to the number of updates. We call this as tree approach. However, when updating on higher level data blocks, for example, at the 8th level, we need to apply threshold bin sort on all data in DP store of 1, 4, 5, 6, 7, and new data 8. It is inefficient. We propose an optimization by using public information in the DP synopsis to reduce the number of records to be processed using expensive MPC protocol. Because DP index can locate boundary of each bin, when we attempt to apply threshold bin sorts only on the newly uploaded data block 8, and then merge it bin-wisely with previous DP stores. However, dummy data in previous DP stores will be accumulated, leading to DP store overwhelmed by dummy records. DP index can additionally locate the boundary of most real and most dummy records. Since dummy records is always in the end of a bin, by estimating the size of dummy using added noise in synopsis, the dotted box contains most dummy. So we can apply threshold bin sort on new uploaded data and the most dummy in previous DP stores to sort the new data and remove extra dummy records. Then we can merge the sorted new data with previous DP store that contains most real to get the DP store 1, 8. Now we only apply MPC protocol to a small part of records, and most dummy records in previous DP store are removed. We compare long shots that use DP structures with a baseline approach that processes each query on all data without a DP structure. DP structure approach includes leave that updates DP structure on disjoint data, treat all the updates DP structure hierarchically, treat opt that additionally update DP store with optimization. First, we want to know how DP structure affects the performance and accuracy of processing queries over time. The observation is that DP structure improves performance and has lower errors than baseline. This is because DP structure can avoid redundant computation and accuracy loss for many ad hoc queries. Next, we want to compare the error over time of tree approach with leaf approach. In this figure, tree approach shows lower errors than leaf approach for large number of updates due to the logarithmic variance over updates. Lastly, we want to know how the optimization of updating DP store affects the runtime and error over time. Updating stores with optimization has a significantly shorter runtime and slightly bigger error than without optimization, because tree opt reduces number of records to be processed using MPC without accumulating many dummies in the DP store. In summary, Longshot designs differentially private storage and index to support more general functionalities with practical performance and a bound leakage using one leakage function, that is DP synopsis. Thank you for your attention.